So now we're back. Hopefully this will be our last video for real this time for section 7.3. And we found that our eigenvalue was 2 plus 3i, and the corresponding eigenvector was 1 plus I. Okay. And we remember from our front page that once we found the eigenvalues and eigenvectors, we let the eigenvalue be the e to the coefficient of the e and the exponent here, and the numbers were the coefficients for our matrix solutions here. Okay, so what we're going to have is this guy, so that's going to lead us to the solution. X vector of t is equal to, we're going to get our vector of 1 plus I times e to the 2 plus 3i times t, which if we do a little bit of work here, we're going to get 1 plus I e to the 2t e to the 3it, okay, which we can then do as 1 plus I times e to the 2t times, using Euler's identity, cosine of 3t plus I sine of 3t. Okay. Now, these act like coefficients or constants here that we can multiply through. So if we do that, if we look at this, our x vector solution is going to be, remember that the x vector solution is the x1 function and the x2 function. So if we multiply this through, we're going to get e to the 2t cosine of 3t, and then we'll get plus I e to the 2t sine of 3t. And then for the bottom one, this one's going to get a little bit longer, but we can do this. So we're going to get, we're going to have to multiply through here because we have a complex number times another complex number. So let's do the real part first. So e to the 2t times cosine of 3t, and the other real part will come from multiplying the imaginary components, I times e to the 2t times I sine of 3t, and the I times I makes -1, so this will be minus e to the 2t sine of 3t plus, and then the next parts we will get the imaginary parts, so we'll get e to the 2t times I sine of 3t. Let me factor the I out of that. And then we'll also get e to the, well, I times e to the 2t times cosine of 3t. And what we're going to do is we're going to break this up. We're going to let the real part be one solution, which we'll call x1 vector solution, not just x1 solution. And if we factor out the I and do a constant multiple anyway, we've got the x2 vector solution. And so we were going to throw on some constant multiples, right? Remember how we did that earlier up here? Okay. So we'll throw on the constant multiples. That can absorb the I here. And so if we do that, we will get the following. That x1 vector is c1 e to the 2t cosine of 3t and c1 e to the 2t cosine of 3t minus c1 e to the 2t sine of 3t, and that's c1 times x1. And if we come over here and do C2 times X2 vector solution, we'll get C2 e to the 2t sine of 3t, and oh, we got to make this guy a vector and this guy too a vector, and C2 e to the 2t sine of 3t plus e to the 2t cosine of 3t. But if we wanted to, we could then remember that this was all the big X vector solution, so we could break them down into his individual pieces and say that x1 of t is going to be the first component here. So we'll get c1 e to the 2t cosine of 3t plus c2 e to the 2t sine of 3t. And then x2 function is going to be c1, let's factor out the c1, and while we're at it, the e to the 2t, times cosine of 3t minus sine of 3t. And then plus this piece here, plus c2 e to the 2t. Let's factor that out. Oops, I did forget the c2 here. There he is, he's there. Plus c2 e to the 2t times sine of 3t plus cosine of 3t. Okay. And that, my friends, is the final solution here to section 7.3. So that's how we handle it if we have a complex number for our eigenvalue. Now you might say, well, Bedrero, the eigenvalues were 2 plus 3i and 2 minus 3i, but as we've seen before, because these are complex conjugates and we've used Euler's identity, and we've got two linearly independent solutions here, the x1 vector solution and the x2 vector solution, anything we'll get from lambda equals 2 minus 3i will be linearly dependent on what we've called the x1 solution and the x2 vector solution already. So I hope that's made sense, and we'll catch you ready for our next video in chapter 10, where we'll learn about Laplace transforms.